There's still three. Oh, I have
They look very nice. There was a hassle I couldn't pay on one of your computers. And just what you need is some funny enabling on your cell phone. And you go in there and it says it wants to send you a code.
I'm not going to be back for a few months. Yeah, I was here for Sarah.
Get started. So, good morning, everyone. It's my distinct pleasure to welcome you to the public portion of Tanmoy Laskar's thesis on the diversity and versatility of gamma ray bursts. Before coming to Harvard, Tanmoy did his undergraduate work at the University of Delhi, and then moved from there to the University of Cambridge, where he did parts 2 and 3 in physics. And during this time, he also explored quite a wide range of research projects, ranging from giant X-shaped radium galaxies to pre-main sequence stars to inverse Compton scattering of the cosmic microwave background. So he explored quite a lot before he even came here to Harvard. Tanmoy came here in 2009 and joined my research group to work on a wide exploration of gamma ray bursts, the most energetic and luminous explosions in the universe. And during his thesis, he used quite a wide range of observations, X-rays, optical, infrared, and I think most importantly, radio observations, both in the centimeter and the millimeter region. Tanmoy's thesis combines two key elements of GRB research. First, an exploration of the actual explosion mechanism and the physics of the gamma ray bursts themselves, And second, the utilization of gamma ray bursts as probes of stars and galaxies in the early universe. And in this talk today, we'll tell you about both of these aspects. But I think the main component of Tanmoy's thesis that's been particularly exciting has been focused on addressing a question that's been open for a long time, which is what are the relativistic jets and gamma ray bursts made of? And at the risk of spoiling the answer, I can tell you that the answer is not sugar and spice and everything. So Tanmoy started making headway into this question by combining the first very detailed radio observations from the expanded Very Large Array, which is now up and running, and sophisticated analytical modeling, much beyond what's been done previously, including by Thesis, of course. So Tanmoy has really been the perfect student for this project. He's a really superb radio astronomer. I think he's one of the few people in the time domain astrophysics community who are pushing the VLA to its limits. And he's also a strong believer in statistical rigor, which is something that's not common in the gamma ray burst field. And combining these attributes of excellent data skills and statistics, he's been exploring quite a wide range of questions. Now, beyond his research on gamma ray bursts, Tanmoy is extremely passionate about astronomy and about teaching in general. As a younger man, he actually built a 6-inch reflecting telescope and a radio receiver to study bursts from Jupiter. And here at Harvard, he's been involved in quite a few teaching efforts, both within the department and also as a tutor in Adams House. And he's received several distinctions for his teaching, a certificate of distinction, a Harvard Merit Fellowship, and a teaching certificate from the Derek Bach Center. As many of you know, Tanmoy is also passionate about music. In fact, he received a secondary field degree in music last year. And he's been an active member and composer for the Harvard Choir. So he's quite a well-rounded person, which is great. So over the past 6 years that Tanmoy and I have worked together, I've come to appreciate him as a colleague for many reasons. His wide range of interests, his candor, his devotion to carrying out very rigorous and comprehensive research, and his, I think, overall love and knowledge of astronomy with a capital A. So as I mentioned earlier, I consider Tanmoy to be a fantastic radio astronomer, and this sentiment was echoed by the National Radio Astronomy Observatory, which awarded him a Jansky Prize for a postdoctoral fellowship, which will be taken to Berkeley starting in August. But today is going to tell us about the diversity and versatility of gamma ray bursts.
Great. Thank you, Ido, very much for that introduction, and thank you all for being here this morning. And a special thanks to those of you who are joining us on the live webcast from around the world. I would not be here today without a few key people in my life. Ido Berger, my advisor, has been a tremendous source of encouragement for allowing me to take charge of my research, for providing the intellectual freedom and stimulation, and at the same time for helping me when I've been going astray. I've learned a lot from you, Ido, and I hope to be at someday half the advisor that you have been to me. I'd like to thank my thesis committee, especially Neil Gerrels, who's come up here from DC to be with us this morning. A special thanks also to my research exam committee, in particular John Hukra, who could not be here today. Thanks also to my collaborators, especially Rangachari and Matt Ashby, for help with Spitzer data reduction, which is another aspect of my thesis that I'll describe to you today. Thank you to postdocs Ashley Zauderer, Rafaela Margutti, and Wenfei Fong for being tremendous sources of support and encouragement over the last few years. I'd also like to thank the Berger Time Domain group for creating a wonderful environment for research. I'd like to take a moment to thank the course instructors whom I've taught. I've learned a lot about being an educator and teacher from you. And I'd like to thank the Adams House science team and resident tutors. It's been great having that opportunity to interact and learn about undergraduate life here at Harvard. Continuing with acknowledgments, I'd like to thank the department administrators for helping me navigate Harvard and the Center for Astrophysics. I'd like to thank my parents for encouraging me always to follow my dreams. And thank you, Mom, for joining me from across the world. And thanks also thanks to them for being willing to not see their only son for 4.5 years as he slaved away at his PhD on the other side of the world. Thank you to my mentors over the past few years. A special thanks to Catherine Rosenfeld. Oh, Catherine, the terrible enabler. I will not start listing all the wonderful things you've done because we will run past the hour. Special thanks to my office mate, Yuchang Zhu. It's been a blast. The last few years have been terrific. Also, Ragnhild Lunan, my classmate, or Dr. Ragnhild Lunan, for being a great source of support. A thanks to my friends in the astronomy department and the astronomy graduate students. I had a few options before starting here, and I chose this department for the astronomy grad student community. And at the end of 6 years, I can say with confidence that I made the right decisions. Thanks, everyone, for creating a wonderful 6 years here. A special thanks to CFA Superintendent Charlie Hickey, who has been instrumental in the smooth functioning of the CFA, something that I have experienced firsthand, including setting up for the talk this morning. Thank you to Anne Matthews for her tremendous source of wisdom and for enabling my other passions, music and composition. I'd like to thank folk from the university choir who are here this morning. They have created a wonderful 2 years of companionship and music making. I'd like to thank everyone, finally, from the choirs that I've conducted in the last few years for not only helping me grow as a choir director, but as a person. Right. The diversity and versatility of gamma ray bursts. I'm here to talk to you today about this exciting source of astronomical transients. But before we delve into gamma ray bursts, let's talk a bit about what gamma rays are. Gamma rays are the most energetic form of light. Their wavelengths are about the size of an atomic nucleus, and most importantly for us, they cannot penetrate the Earth's atmosphere. Now this last point is important because it means that before humans sent satellites into space, we had no way of knowing what the sky looked like in gamma rays. Our story begins in the 1960s at the height of the Cold War. During this period of an arms race between various countries of the world, nuclear weapons were being tested all over the planet. Now it is quickly realized that some parts of the world must remain sacrosanct to prevent nuclear fallout from spreading all over the planet. To this end, a treaty was signed in 1962 between the USSR and the West. The provisions of this treaty were to prevent nuclear explosions in the Earth's atmosphere and in the oceans. To enforce this treaty, satellites were sent up by the United States, and the aim of these satellites was to look for explosions in the Earth's atmosphere and oceans. Now, these satellites did not find evidence for nuclear explosions in space, but what they found instead were flashes of gamma rays coming from outer space. The existence of these events was announced in a paper in 1973. These flashes were so powerful that they completely outshone the entire sky in gamma rays. It was a long time before people realized what these were. In the Compton Gamma Ray Observatory, launched in 1991, found several thousand of these sources distributed uniformly across the sky. Now this was interesting because it suggested that these sources were isotropically distributed around the sky, with no regard for the plane of the Milky Way galaxy. Now this meant that these sources were either coming from the halo of the Milky Way galaxy, or they were coming from far distances, from other galaxies. Now the problem with figuring out which of these was really the case was because gamma rays, being the most energetic form of light, are also extremely hard to localize. Here is an example of a gamma ray airbox. An event happened somewhere in here. If we look in the same region in the optical light, we find, yes, several thousand visible light sources. And it is impossible to tell which of these sources was the cause of the gamma rays. It wasn't until 1997 that the first fading X-ray and optical counterpart to one of these sources was discovered. An optical spectrum of this optical counterpart revealed features in the spectrum that suggested that this source was moving away from us at about half the speed of light. Now, this is not because the source is moving away from us at that speed, but it's because it's participating in the expansion of the universe. In other words, it is at a cosmological distance, and it's actually in another galaxy. Now, this is particularly exciting because it means that these sources are extremely energetic. How energetic? Well, we'll see in the next few slides. We now know that there are two classes of gamma ray bursts. The long-duration gamma ray bursts, which are believed to be from the deaths of massive stars at the ends of their lives, and the short-duration gamma ray bursts, which are believed to be formed from the merger of compact objects such as two neutron stars or a neutron star and a black hole. In the rest of my talk, I'll focus on long-duration gamma ray bursts. These are the events that are formed from the catastrophic deaths of massive stars. Long-duration gamma ray bursts are located in star-forming regions of their host galaxies, and so we know that they are associated with massive stars. In addition, the smoking gun evidence for their association with massive stars is that they have been found to be associated with supernovae. And supernovae are clearly deaths of massive stars. These are the most energetic explosions in the universe, with energy budgets of about 10 to the power of 54 ergs. Now, this is quite a fantastical number. It is about the rest mass of the sun turned completely into radiant energy in a few seconds. Because of this extreme brightness, these extreme energy budgets, gamma ray bursts can be seen out to the edge of the visible universe. Their short durations, combined with this large energy budget, means that they are relativistically beamed. They move at the jets from these events move at relativistic speeds toward us, and that they are powered by a compact central engine, such as an accreting black hole. Now, this is what we know about gamma ray bursts, but it raises several interesting open questions. And here are a list of a few open questions that I aimed to answer over the course of my thesis. What are gamma ray burst jets made of, and how fast is the outflow from these events? What causes the great diversity of gamma ray bursts? We know that the universe evolves as you go to higher redshifts, at greater distances, at earlier times. Do the progenitors of gamma ray bursts also evolve as the universe does? And what can the great versatility of gamma ray bursts be used to tell us about the infant universe? Now, these are questions that I've answered over various research projects. I will tell you today about the first and the last of these research projects in this list. Let us therefore begin with the first question. How fast is the gamma ray burst outflow, and what are these jets made of? Gamma ray burst jets are extremely relativistic explosions, and they are great laboratories for studying relativistic shock physics. Now, what is a shock? Well, here's an example. This is a bullet moving through air captured on a shadowgram. The line that you see in front of the bullet is a shock wave moving through air. This shock wave separates the unshocked region, the air that has no idea that there's a bullet coming at it, from the shocked medium, which is the region that has discovered, oh, something just went past really fast. That region has been compressed and heated by the shock wave. Gamma ray burst jets are like bullets being launched from the central engine, expanding out into space. Regions within the jet interact with each other. They crash into each other, producing shock waves. These shock waves produce the initial flash of gamma rays. This is what the Vela satellite saw, and how gamma ray bursts are detected to this day. As the jet interacts with the surrounding medium, it sets up this blast wave shock, this forward shock, just like a bullet does as it moves through air. This shock wave compresses magnetic fields and amplifies them. It also accelerates electrons to relativistic speeds. These electrons then gyrate in these magnetic fields and produce synchrotron radiation. This synchrotron radiation is what powers the long-lasting X-ray, optical, and ultraviolet and radio wave afterglow. A little more about the synchrotron spectrum, because this is how we see these sources in our sky. This is a plot of brightness as a function of frequency of light. This is where the radio waves and X-rays are located, for instance. The afterglow of a gamma ray burst, the radiation coming from the blast wave shock, spans a long range of frequencies all the way from the radio through to the X-rays. The spectrum is determined by 4 characteristic numbers: 3 break frequencies, which separate the various power law components of the spectrum, and a peak flux. These four components together they completely specify the spectrum. So if you measure the spectrum and you measure these components at a given time, you know everything there is to know about the spectrum. There are correspondingly four unknown quantities. And measuring these four quantities gives us important information about the energy of the explosion, the density of the surrounding medium, and the amount of energy of the shock that goes into accelerating electrons, and the fraction that goes into compressing and magnifying magnetic fields. This brings us back to the open questions. How do we use all of this to study gamma ray burst physics? Well, there is one more key ingredient left, and that is the concept of the reverse shock. Here is an example of, this is a video. So you will see, as I play this video, cars moving in a circle. These cars they start out spaced equidistant from each other. But as time progresses, you will see that the shock builds up, cars in front slow down, and cars at the back catch up. And this shock wave propagates backwards along the ring. A similar feature happens in gamma ray burst jets. Gamma ray burst jets, as they propagate into the surrounding medium, create the blast wave shock. The front of the jet hits the surrounding medium and slows down, and then the back of the jet catches up with the front, and so the shock wave goes backwards through the jet itself. Now this shock, called the reverse shock, is the only direct means of probing the jet itself. And this is important because this is the way that we can determine whether the jet is what its composition is and how fast it's moving. In particular, there are two mechanisms, there are two particularly favored models for what the jet is made of. One, that a jet is made of baryons, protons, electrons, tables, and chairs, regular matter. Or that they are dominated by magnetic fields. And it turns out that only if the jets are dominated by baryons, by regular matter, do we expect the signature of a reverse shock. What is the signature? Well, a reverse shock, just like a forward shock creates a synchrotron spectrum, a reverse shock does exactly the same thing. So here is an example of what this forward shock spectrum looks like. I showed you the various synchrotron components. Well, they're actually smoothly connected at those power laws. A reverse shock is very similar. It also creates similar synchrotron radiation, compresses magnetic fields and accelerated electrons, produces synchrotron radiation. The difference is that although the blast wave shock propagates into the surrounding medium as long as there is material for it to plow into, the jet has a finite thickness. Therefore, when the reverse shock crosses the jet, it's done. And it leaves behind this rapidly cooling population of electrons. Therefore, the spectrum of the reverse shock cuts off at what is called the cooling frequency. And there is no contribution, typically, of the reverse shock in the X-ray band. Now, this spectrum is a snapshot at a given time. It's a snapshot at a time when the reverse shock has just crossed the ejector, typically a few minutes after the explosion. Really, when the jet expands and the shock expand and the population behind the jet cools, these shocks evolve with time. The spectrum evolves with time. I'm going to show you a movie now of how these shocks evolve. One important thing to note is that there are two possible scenarios for what the surrounding medium looks like around the star. And in fact, depending on how the spectra evolve, we can tell what the surrounding medium is like. There are two possible scenarios. Either the medium has a constant density, which is what you might expect if an event happened in sort of a random place in a galaxy. An alternative is that that medium is sculpted by the winds of the progenitor star. We expect that the stars that create these events are extremely massive and that they have, therefore, strong winds. And therefore, we expect that the surrounding medium has a density profile which falls off as 1 over r squared, 1 over distance squared from the progenitor. And as we see these spectra evolve with time, we can see which of these is the case. So I'm going to play this movie now, and you will see these spectra, these shocks evolve with time. Note that at early times, at a few minutes after the explosion, there is some very minimal contribution of the reverse shock in the optical. There is none in the X-rays. There is a bright flare in the millimeter waves. and there is significant contribution in the radio waves. It's very challenging to observe in the radio waves at these times, but I'll show you some examples of where we've been able to do just this. As time progresses, the peak of the reverse shock moves to lower and lower frequencies, eventually showing up in the radio waves at a few hours to about a day. At the same time, the peak of the forward shock moves to lower frequencies, goes through the optical, shows up in the millimeter waves at about a day or so, and eventually it arrives in the radio waves. Of course, this depends upon the exact properties of the progenitor, and once we determine where all these frequencies are, what the spectrum looks like, we can measure all those properties of the progenitor. Now, to study this, we require observations across a broad range of frequencies. As I showed you, these spectra evolve with time across a broad range of frequencies. So we like to observe in the X-rays, the optical, the millimeter waves, and the radio waves. We'd like to pin the spectrum down at a given time, and we'd like to see these spectra evolve with time. Therefore, we have a comprehensive multi-wavelength target of opportunity program here at Harvard, where we follow up interesting gamma ray bursts detected with the Swift and Fermi space telescopes in the X-rays and in the optical. So Swift has great X-ray coverage. The optical come from Gemini, Magellan, and MMT on the ground. At lower wavelengths, we observe with the Very Large Array, which is something that Edu alluded to in the introduction, and I'll have a lot more to talk about VLA in a moment. And in the X-rays, we also trigger with the Chandra and XMM telescopes when, I'm sorry, I have to take this for a second. Hey, hi Ashley. No, I haven't, I was in the middle of, sorry, what's the declination again? Gamma ray bursts are extremely fickle objects. They have no regard for whether you are directing a concert in a choir or singing somewhere, or whether you're in the middle of a thesis defense. Anyhow, that was a false alarm. This is how we collect the data. These events happen anytime, and you have to be ready to collect observations. Once you have the observations, the next important thing to do is to analyze them statistically. To this end, I have developed a comprehensive, statistically robust set of tools. This is the first time that some of these various things have been put in the same place. So let me briefly show you what this software does. The gamma ray burst multi-wavelength modeling software takes into account several intrinsic features of gamma ray bursts, such as the full broadband spectral evolution, the 3 break frequencies of the reverse shock and the forward shock, and the evolution of these frequencies at time, the possible orderings of these various break frequencies. I also account for jet breaks. What is a jet break? Well, gamma ray burst jets are beamed towards us. They are not completely isotropic. The energy is radiated in a tiny cone, which is pointed at the observer. Now, since these jets are moving relativistically, an observer only sees a small patch of the jet of an opening angle that corresponds to 1 over the Lorentz factor, theta corresponding to 1 over gamma. Now the jets are slowing down with time, and therefore the amount of the jet that we can see grows with time, until eventually we can see the entire jet, and suddenly there is no more jet. At that point, the light curves, the flux as a function of frequency at all observing wavelengths, plummet. Measuring this time, the jet break time, allows us to determine the opening angle of the jet, and thereby determine the true energetics of the explosion. Eventually, these jets slow down enough that they become quasi-spherical. At that time, the jets become non-relativistic, and this is a transition that impacts typically the radio waves, because this happens at about 100 days or so, and around that time, the gamma ray burst is typically visible in the radio waves. The afterglow is typically faded at all other wavelengths at that time. There is an additional physical process that happens in the X-rays. The electrons that are producing the synchrotron radiation that powers the afterglow also scatter off their own radiation and thereby cool by a process known as the inverse Compton process. This is a phenomenon that affects the X-rays, and it needs to be taken into account. On the side of extrinsic effects, GRBs shine through the medium of their host galaxy And these galaxies typically are star-forming. They have a lot of dust. And this dust causes a decrement in the amount of light that is visible in the optical and in the ultraviolet. Similar effects happen as the light propagates through the Milky Way, and this is something that needs to be taken into account as well. As the GRBs shine through medium between galaxies, as they go off in a distant galaxy, the light propagates through the intervening medium, the intergalactic medium. The IGM also has a lot of neutral hydrogen. This neutral hydrogen is able to absorb a lot of the light. And this is an effect that typically impacts gamma ray bursts at high redshifts, which I also take into account. An interesting effect that is visible in the radio is interstellar scintillation. Scintillation is the twinkling of light in the radio waves as light from the GRBs is scattered by electron density inhomogeneities in the ISM, the interstellar medium, or the Milky Way. This is very similar to the twinkling of starlight as visible light propagates through the atmosphere of Earth. And finally, I incorporate all of these into a robust statistical framework using Markov chain Monte Carlo that allows me to determine not just the values of the physical parameters, but the correlations between these physical parameters, and to make sure to find out where there are hidden degeneracies in the model. Right, that brings us to a close of the introduction to this segment, and let us now talk about how we determine the properties of the jet, in particular the speed of the jet. These are the only equations I will show in my talk. The quantities on the right are properties of the blast wave shock. They are the frequencies and the peak flux of the blast wave shock. On the left, the quantities correspond to the reverse shock. They are connected by a single quantity, gamma, which is the Lorentz factor. The Lorentz factor, of course, just depends on the velocity. Therefore, if you measure the Lorentz factor, you have measured the velocity of the jet. And this is one of the key open questions. What is the speed of the jet? Now note that this system is over-constrained. There are 6 measurable quantities, there are 3 equations, and there is 1 unknown, gamma. Therefore, if you measure all of these properties, all of these parameters, they had better all be consistent. And you should make sure that you get the same value of gamma from all of these equations. Has this been done before? Well, this is the state of the art before I started my thesis. Here is an example of a gamma ray burst from 1999. Here is what I was calling a light curve, flux as a function of time at a given frequency, here in the optical R band and here in the radio waves. This dashed curve and these points are radiation that is attributed to the blast wave shock. This is seen very frequently. The interesting point to note are these 5 data points that are above this interpolation. And this suggests that there might be some additional radiation coming from somewhere else, perhaps a reverse shock. And actually, if you propagate that to radio waves, it looks like there is some contribution of some additional component in the radio waves. So in the radio waves, these are 4 upper limits and 1 detection. Okay, so I suggested that what we would like to do is decompose the spectrum of a gamma ray burst into the reverse shock and the forward shock. We'd like to see this evolve with time. Can you do this with this data? Not really. Can you measure the Lorentz factor? Well, not really, because you really need to measure these equations, and that has not been possible with these data. So what we'd really like to do is we'd like to have a multi-wavelength spectral energy distribution, light as a function of frequency, flux as a function of frequency. We'd like to decompose that spectrum into reverse shock and forward shock. We'd like to see that spectrum evolve in time. We'd like to show that one of those components is evolving like a rapidly cooling of population of electrons, like a reverse shock might evolve. We'd like to show that those spectra are related together, just like a reverse shock and a forward shock should be related. And from all this, we'd like to show that we can derive a self-consistent value of the Lorentz factor. This has not been possible in the past because typically at a few days, the reverse shock peaks in the radio, and radio telescopes has just not been sensitive enough until now. These are observations of a gamma ray burst from 2 years and 2 days ago. Here are optical and X-ray observations of this GRB. This dashed line is a plot of a forward shock model that fits the optical and X-rays pretty well. This data was taken at 0.67 days from the Swift satellite. to orient us, the radio waves are out here, the X-rays are out here, here are the optical and millimeter waves. Now, where we obtained radio observations at the same time, at 0.67 days. Now, this is a great advancement because we have not been able to take radio data at a few hours after a gamma ray burst. And here is where the data show up. They are clearly above what you might expect from just the forward chuck alone. Right, we have observations at 2 days. And interestingly, the X-rays and optical fade. And that amount of fading is enough in this case to tell us that the progenitor environment is not a constant density environment, but has a density that falls off as 1 over distance squared. And that therefore, this is a clear evidence that the progenitor of this object was a massive star. We have radio observations at 2 days again. Here is an entire spectrum in the radio waves. Something like this has also not been possible in the past. The observations with the Very Large Array at multiple frequencies have been very challenging. And this is because of recent upgrade with the Very Large Array. We've been able to obtain data at spanning the entire frequency range from 1 gigahertz to 40 gigahertz at multiple frequencies, allowing us to make spectral energy distributions like this. So we can show that not only is the data brighter than what you might expect, we can see a spectrum in the radio waves. And that spectrum is clearly has a different index. It is falling with frequency as opposed to rising with frequency. Here are data at 5 and 10 days, respectively, in the optical. And here are the radio observations. This dip, in case you were wondering, is due to extinction, absorption by dust in the host galaxy. Now, this is very interesting. Let's take a look at the data at 2 days. That's the green model. And let's assume for a second that this radiation is powered by synchrotron radiation. And this is a synchrotron spectrum with its 3 Blake frequencies just put on that figure. And if we add those 2 spectra together at 2 days, that's what we get. Now, that fits the data very well. What we do now, what I did after this, was take this spectrum, this dashed spectrum, and evolve it backward in time, as one might expect a reverse shock to have evolved. And that's what I get at about 0.67 days. Evolving it forwards in time, that's what I get. Now, this is a small fraction of the data I collected. I'd like to show you now observations of light curves, flux as a function of time, from the X-rays through the ultraviolet, optical, millimeter, and radio waves. Hold on to your seats. These are observations of the X-rays. The X-rays are dominated by the forward chuck component. The data out here, you can ignore this. These are dominated by the gamma ray emission from the prompt emission, from the initial flash of gamma rays. This is the tail of the gamma ray emission. This is observations in the ultraviolet, and all the data after 0.1 days can be fit with the same forward shock, the same blast wave shock model, as can be used to fit the X-rays. Interestingly, there is some additional flux in the ultraviolet at before 0.1 days. This dashed curve is what you would expect. These are the same dashed curves from the previous model. These are the wind model. And these points are above that model. What I did was take that dotted curve from the previous model, the green SED that I fit, spectral energy distribution, and propagated it back now to the optical, the ultraviolet, and all the way back to 0.1 days, and to a few thousand seconds. And that's this dotted curve. So that same dotted curve that fits the radio data at 2 days also fits the ultraviolet data at around a few thousand seconds. The same story in the optical. There are 2 components. And the radio waves are entirely dominated by this second component. Don't believe me yet. If these 2 components are actually part of a double shock system, then they must be related through these equations. It turns out, I'm not showing you the numbers, but it turns out that if you do these calculations, we measure all of these frequencies for the first time. We've measured all the frequencies on the right and all the frequencies on the left. Calculating those numbers, it turns out that they all match within a factor of 2. And they consistently give the same value of the Lorentz factor. What is that Lorentz factor? It is 130, which corresponds to 99.997% the speed of light. This is the first direct measurement of the relativistic expansion of a gamma ray burst jet a few hundred seconds after the explosion. By measuring the properties of the forward shock, I was able to determine the kinetic energy of the ejecta, and it turns out that in this case it corresponds to about the rest mass of Saturn turned completely into radiant energy. I also determined that in this case the progenitor was a massive star with a relatively low mass loss rate as what might be expected for a Wolf-Rayet star. Wolf-Rayet stars are stars that are believed to be progenitors of these events. And for Wolf-Rayet stars in the Milky Way, they typically have mass loss rates of about 10 to the power minus 5 solar masses a year. This event had a much lower mass loss rate, and I actually believe that this low mass loss rate and the corresponding low density environment is necessary for the creation, for us to be able to detect a reverse shock, because it results in what is called a slow cooling reverse shock, resulting in a shock wave that is detectable out to later times. I'd like to emphasize here that this is the first time that this observation has been done, a measurement of the Lorentz factor of a jet has been made so close to the explosion. There has been one case where a gamma ray burst jet has been shown to be moving relativistically. That was in 2003, and that was done months after the explosion by very long baseline interferometry resolved observations of an expanding jet. But this was done at 100 seconds, and that tells us the initial Lorentz factor of the jet. This particular event was so exciting that we obtained observations, analyzed the data, and published a research paper in 13 days. This result was subsequently verified by two other research groups a few months later who came to the same conclusion using the same data. To summarize then, I've studied the afterglow of this gamma ray burst in unprecedented detail. There is unambiguous evidence for a reverse shock signature, which implies that in this case the ejecta are baryonic and that they are not dominated by magnetic fields, because remember, if there is a reverse shock, if we find a reverse shock, that suggests that the ejecta are dominated by baryons and not by magnetic fields. For the first time, I have measured all the spectral properties of the reverse shock, compared it with the forward shock, and have been able to determine the Lorentz factor of the explosion. The combined model of the reverse shock and the forward shock matches all the data across 3 orders of magnitude in time and 9 orders of magnitude in frequency. Right, that brings me to the end of this part of the talk. I'd like to move on to the second open question that I was talking about, which is gamma ray bursts and the infant universe. Gamma ray bursts can be used to study galaxies that they go off in. Now, galaxies are extremely dynamic systems. They are large reservoirs of gas and dust. The gas turns into stars, the stars go boom, and the spewed out material, these metals, what astronomers call metals, are anything but hydrogen or helium. These metals turn, I'm sorry to the chemists in the audience, these metals turn into planets and eventually into us, into people. Now, in this great cosmic scheme of recycling, there is an interesting relation that is observed between the stellar mass of a galaxy, the amount of mass of a galaxy in stars, and the amount of metals that the galaxy has produced. This is the so-called mass-metallicity relation of galaxies. This relation has been seen in the nearby universe. Here are observations of several thousand galaxies from the Sloan Digital Sky Survey. These are, on the x-axis are stellar masses, the amount of mass of the galaxy in stars. On the y-axis is what astronomers call metallicity, here measured using rest frame observations of emission lines. Emission lines allow us to measure quantities like the amount of oxygen. And the ratio of the amount of oxygen to the amount of hydrogen is what is plotted here and is called the metallicity. This relation is now, this is an example of the relation in the nearby universe. Interestingly, this relation is also visible at higher redshifts. In fact, it appears to evolve to lower metallicities as you go to higher redshifts at a given stellar mass. This is, it sort of makes sense because as galaxies evolve with time, they make more and more metals, and so the metallicity of the environment goes up at a given stellar mass. But it raises the important question as to how do the galaxies know where to fall along this relation? For this, we'd really like to figure out when is this relation first set? When does it first appear in the universe? For this, what we really like to do is push this relation out to higher and higher redshifts. Now, this becomes challenging at higher redshifts, and that's because, well, firstly, you need to find these high redshift galaxies. And that's very difficult because these are very faint sources. Additionally, you don't just have to find the galaxies, you have to take a spectrum of the galaxy. Because a spectrum is, in this case, what is required to measure something like the oxygen abundance. And galaxies become very faint, and spectroscopy becomes extremely challenging. The various spectral lines move into different observing bands as observed on our Earth. And it really multiplies, it doubles or triples the observing time required to get these observations. I'll now show you how one can use gamma ray bursts to deal with these problems and to solve this particular open question. Regarding metallicities, gamma ray bursts, owing to their extreme luminosities, as they shine through the host galaxy, they act as beacons. These powerful lighthouses have very simple synchrotron spectra, as I showed you on the previous slides. Imprinted on this otherwise featureless synchrotron spectrum are rest frame absorption features from the interstellar medium of the host galaxy. Here's an example of a gamma ray burst at redshift of 4. Redshift of 4 is beyond all the events that I was showing on the previous slides, all the galaxies I was showing on the previous slides. And this object, this afterglow, this optical afterglow, was about as bright as a typical faint star in the Milky Way for a few seconds, a few minutes, allowing us to take a high signal-to-noise spectrum like this. Absorption features from neutral hydrogen in the galaxy allow us to measure the amount of hydrogen, the column of neutral hydrogen along the line of sight. And absorption features from rest frame ultraviolet lines, such as sulfur, allow us to measure the quantity of metals. The ratio gives us the metallicity. In this case, the metallicity is about 15% of the sun. So that's how you measure metallicities. Now, the exciting thing here is that you don't need to take the spectrum of a galaxy. You can take the spectrum of a bright afterglow, and then you know, aha, there is a high redshift galaxy in that direction at those coordinates. And I have already measured the metallicity by taking a spectrum in the optical, where already our current instruments are extremely sensitive. To measure the stellar masses requires a different technique. Here is an example of an optical afterglow. This is a field of stars, and then I'm marking here with the red circle an optical afterglow of a gamma ray burst. Located on the left is an observation from the Spitzer Space Telescope. And you can see that some of these stars, these objects, correspond to some of these objects on the two slides. I'm marking the region of this afterglow on the left, and you can see that there's a source in the field. Now, the advantage of Spitzer observations is that the advantage of having an afterglow is that as the afterglow fades, it reveals in its location the host galaxy. Then you can go back and determine the stellar mass of the host galaxy. To determine the stellar mass, one needs to measure the rest frame optical light. And that is because most of the stellar mass of a host galaxy is in the old stars. Old stars radiate predominantly in the rest frame optical. And at high redshifts, which is where we'd like to measure this relation, the rest frame optical is shifted into the observer frame near and mid-infrared. And Spitzer Space Telescope is the current observing instrument, the telescope that is able to take observations in the near and mid-infrared. And so if we take observations at those frequencies of host galaxies, we can determine the total stellar mass. Zooming into this region, we can actually see that the afterglow allows us to pinpoint the location of the host galaxy to such precision that in this case, we know that there is actually a contaminating foreground star that I am then able to model and subtract. And what remains is the faint host galaxy of the gamma ray burst. And using this observation, I'm able to determine the stellar mass. What is the stellar mass? Well, in this case, it's about 25% of the Milky Way, the stellar mass of the Milky Way. This is an example. I did this for a sample of gamma ray bursts above redshift 3 to see if I can push the relation of the mass-metallicity relation of galaxies to beyond redshift 3. I'd like to show you on the next slide the results of the stellar masses that I observed. This is a plot of stellar mass versus redshift. The purple points, the magenta points, are low redshift gamma ray burst host galaxies. The orange and red points are galaxies in intermediate redshifts that have also had the stellar masses measured from a different technique. And the bars and the limits here are events in my sample. I have a detection fraction in my sample of about 25%, and so there are some upper limits, and I'm able to take those upper limits into account statistically. As Ido told you, I love statistics, and so I'm able to take all those into account. For comparison, for a level of comparison, this is where the Milky Way stands, and this is where the satellite of the Milky Way, the Large Magellanic Cloud, stands. What I'd like you to take away from this slide in particular is that these gamma ray bursts, host galaxies, these gamma ray bursts allow us to find host galaxies all the way out to redshifts of 6 or beyond. And this is an excellent technique for finding these high redshift galaxies, and then you can go back and measure the amount of the stellar mass of these galaxies. Some of these galaxies are pretty massive, and those are the ones that I do detect. There's a large fraction of upper limits. I then stack the Spitzer observations of those upper limits. That's still an upper limit. There was a non-detection, and that is this upper limit. This green point, therefore, corresponds to the mean stellar mass of the galaxies that went into the stack. And that limit is comparable to about the mass of the Small Magellanic Cloud. Right, we have the masses. We have the metallicities from absorption spectroscopy. Let's put them together. Here is what we find. Is that a gamma ray burst? Right, so the metallicity as a function of stellar mass is what we've been waiting for. Here is the Milky Way and the Large Magellanic Cloud for comparison. And here are the relations at lower redshifts. And these are where the GRBs stand. This is a bin of all the detections, and this is the bin of the upper limits of the stack in particular. What you should note here is that the stack not only is at lower stellar mass, which is of course what you would get from the photometry, from the observations, but also that the objects that went into the stack have systematically lower metallicities. Now this is the first hint of a mass-metallicity relation at redshifts beyond 3 or 4, all the way out to redshifts of about 6. To summarize then, I've used afterglow absorption spectroscopy to measure the metallicities of gamma ray bursts, and this technique allows us to measure metallicities independent of the brightness of galaxies. The location of the afterglow allows us to go back and find the host galaxies, and thereby to measure the stellar mass using Spitzer observations. Putting those two together, I have the first mass-metallicity relation of galaxies beyond redshift 3, and there's a first hint that this relation continues to evolve at redshifts as you go beyond redshift 3. Now this brings me to the conclusion of the talk. I'd like to end with the results of these studies. These are the questions that I posed at the beginning of the talk, and these are the answers that I have demonstrated to you. How fast is the outflow from a gamma ray burst jet? Well, at least in this one case, I've measured the relativistic expansion, and I found it to be a Lorentz factor of 130, corresponding to 99.997% the speed of light. What are the jets made of? At least in this one case, it's clear that they're dominated by baryons. What do the versatile gamma ray bursts tell us about the infinite universe? They allow us to measure the properties of galaxies at high redshifts, and I've demonstrated to you the first hints of a mass-metallicity relation of gamma ray burst host galaxies above redshift of 3. Now I know you're dying to know the answers to the other questions, and I'm sorry I don't have time to go into those, but what I'll do is just show you the results that I find. What causes the diversity of gamma ray burst afterglows? And the answer, I believe, is the distribution of ejecta energy as a function of Lorentz factor within the ejecta. Ejecta are, I described to you as bullets. It turns out, from all the observations that we'll be getting, that is a simplified picture. And that, in fact, it's not just one bullet, but many bullets with many different Lorentz factors. And the amount of energy in the different bullets actually tells us something about, actually impacts the light that we see and tells us something about the central engine. Does the progenitor population evolve with redshift like the universe does? There is no evidence yet from my studies, at least out to a redshift of 9.5. And that, a redshift of 9.5, redshift of 10 or so, is when the universe was a 10th and 11th of its present size. That was a long time ago. I'd like to end with a few notes to future work along these lines. In the next few years, we expect to receive several exciting triggers from the Swift Space Telescope and from Fermi. I am part of a collaboration that has just been approved time at the Very Large Array. So the Swift will have great coverage in the X-rays. At the other end of the wavelength range, we need radio observations. And so I'm a part of a collaboration that has just been approved, a program on the Very Large Array, which started in February, for observations of gamma ray burst afterglows. In the millimeter waves, ALMA, the new upcoming millimeter telescope, which has started science observations, will be great for catching the peak of the reverse shock as it passes through the millimeter. ALMA observations at early times are extremely challenging. They are technically not yet quite feasible. And so we do have a proposal for ALMA observations, and we'll see if we get the time, and we'll see what happens there. And that is a really exciting new frontier in gamma ray burst observations. In the optical, I'm collaborating with the Liverpool Telescope and with the Las Cumbres Observatory Global Telescope Network for follow-up in the visible bands at both early times for catching the reverse shock and at late times for catching the forward shock. And as you know, observations of both are extremely essential for separating the two. These programs have already yielded some really exciting results. I'm going to flash a slide with some of these observations. Here are 2 gamma ray bursts observed with the VLA in the last year or so. Now, as I mentioned to you, one of the wonderful things that the Very Large Array upgrades in the last few years have enabled is multi-frequency coverage within the radio, allowing us to measure spectral energy distributions within the radio itself. And these observations now allow us to find these really phenomenal spectra that have something like this has never been seen before. And what do I mean? Well, here is a multi-component spectrum in the radio itself. These points fall along a blast wave shock, and these points clearly are above the extrapolation of that blast wave shock. A similar thing happens in this event, and this spectrum is extremely challenging to fit because it's flat across over an order of magnitude, about an order of magnitude and a half in frequency across the radio. In the past, what people have done is observe at a single frequency, and then all of this information is lost because you don't know what the spectrum looks like in the radio. And so by following up at multiple frequencies at early times, we are getting these really phenomenal observations. And I have multiple frequency SEDs of these objects, and I'm working on the interpretation, so stay tuned. These observations are not only exciting because of these wonderful spectral energy distributions, note the redshifts. These are extremely far events, and at the time of these events, the universe was only 1 billion years old. Talking about the early universe, future Spitzer observations, current Spitzer observations of GRB host galaxies will allow us to probe the mass-metallicity relation even further. In particular, I'm part of a collaboration that has just observed a complete sample of gamma ray burst host galaxies. I had about 25 events on the previous slides. Well, that sample has now been quintupled, allowing for great statistics and for allowing us to divide the mass bins even further and see what the relation looks like at redshifts greater than 3. Looking even further beyond the Spitzer Space Telescope, the James Webb Space Telescope, which is coming online in the next few years and is currently scheduled to be launched in October 2018, will allow us to measure the stellar masses of not just the galaxies that have been detected by Spitzer, but even all the objects that were non-detections on the previous slides, allowing us to not just have mass bins, but actually get a full mass-metallicity relation. In addition, James Webb Space Telescope, the JWST, has a mid-infrared spectrograph. That spectrograph will allow for observations of rest frame optical spectra. And from those optical spectra, we will get emission line diagnostics, emission line metallicities. And for the first time, we will be able to calibrate emission line diagnostics metallicities from emission lines with the absorption lines that we get from the afterglows. And this is something that has really not been done except for one event at a redshift of 2. Right, that brings me to the end of this presentation. Thank you very much for your attention.
Thank you, Tanmoy, for a great talk. Time for questions. Neil.
Well, those are beautiful multi-wavelength analyses that you've done. Could you comment on why we see reverse shock so strongly in some bursts and much less or not at all in others?
that is an exciting question. The question is, for people who are listening elsewhere, why do we see reverse shocks only in a few cases? And that is a question that I've been asking myself as well. So one of the possible reasons is that perhaps one needs a low density environment. And only in the cases where you do have a low density is a reverse shock in the slow cooling regime, and therefore lasts for much longer. Another possibility is that reverse shocks do exist, they are weaker, and we just haven't had follow-up at the right times to detect them. And I already showed you a couple of examples where it looks like the reverse shocks are more frequent than we have thought in the past. So it'll be great to actually do the statistics and figure out what is the key determining mechanism. Are all jets made of baryons? Are some jets made of baryons? Are some jets dominated by magnetic fields? And this really requires observations of reverse shocks across a large number of objects to really figure out what is the driving cause. So I'm looking forward to answering that question in the next few years.
Near the end, when you showed the new double-humped radio data, I was wondering, do you ever see maybe like 2 reverse shocks simultaneously? And would it look like that?
Allow me to bring that slide up so that we know what we're talking about. So the question is, in this case, we see a double-humped feature. Is it possible that there are 2 reverse shocks, and what might you expect? Interestingly, it's very interesting that you asked this question, because in this event, if you propagate these 2 shocks forward, if you look at the data, this is the data at about 1.5 days after the event. We have radio observations of this event multiple times. At about 16 days, it looks like there's another high frequency component that shows up. And it's possible that in this very event, there are actually already 2 reverse shocks. Why might you expect 2 reverse shocks? What would that mean? And it's possible that the ejecta, as I mentioned, are not simple bullets, but there are multiple layers of ejecta. As the first set of ejecta interact with the surrounding medium, there's a reverse shock that goes through it. Then the second ejecta catches up, dumps its energy into the blast wave, and there's a reverse shock that goes through the second set of ejecta. So it's possible that there are 2 humps created by 2 reverse shocks, 2 rapidly cooling populations of electrons, and perhaps once I'm done with this analysis, it'll turn out that in this case, that is what is exactly happening.
So how about the circumpolar material? So you said that it would fall, you expected it to fall smoothly, but if you had several episodes of losing the outer materials of the stars, you might expect that there could be overdensities at various places, and would that affect the observed properties?
Great. The question is, massive stars at the end of their lives shed off. We've seen this from, say, Eta Carinae and other massive stars in our galaxy. They shed these enormous outbursts, layers of material. And when that star explodes, you expect the shock wave to run into these layers of material. What would you expect to see? Well, there are some claims that you would expect a brightening in the radiation. There are also other claims that actually the density enhancement that you need for a brightening is actually very severe. You need an enhancement by about a factor of 100 to see any significant brightening. Interestingly, the amount of the light in the X-rays, which is typically what is extremely well sampled at the time that this shock is plowing through the surrounding medium and catching up with these density inhomogeneities, the light in the X-rays is independent of the density of the environment. It's a curious factor of the synchrotron radiation. And so it's impossible to tell using just the X-rays whether that's happening. But radio observations can actually help us constrain that, because they constrain the self-absorption frequency, which is very sensitive to the density. So it remains to be seen why we don't observe these. It turns out, I didn't tell you this, it turns out that in most cases, evolution looks smooth. There are situations where you see bumps, but they cannot be attributed to these density enhancements. So we're still looking for those signatures.
You had this very interesting discussion of the mass-metallicity relationship to high redshift. But are you sure that the galaxies that have gamma ray bursts and they produce those stars are characteristic of the bulk of the galaxies? You might compare the part at high redshift to the part at low redshift, but my question is, whether the presence of a gamma ray burst is selecting a different population of galaxies.
The question is, are gamma ray bursts selecting a particular class of galaxies, a particular kind of galaxies, and thereby perhaps the relation that you see is in a sense perhaps biased, because the GRBs, maybe they need a particular kind of galaxies. In the research that I did, I compared the galaxies that these gamma ray bursts happened in with the field galaxy populations, galaxies at lower redshifts, and I determined that there was no evidence for differences in the stellar masses of these galaxies statistically compared with the field galaxy samples. Additionally, there has been a claim, and with very good reason, that gamma ray bursts only happen in low metallicity environments. The reason for this claim is because to form a massive star, for a massive star to collapse and to produce these jets, you need it, when it collapses, to have high angular momentum, because you need to create an accretion disk in this core. Just as a black hole forms, you need an accretion disk to power the jets. You need high angular momentum. For this reason, the star, before it dies, must not lose all this angular momentum it has. Stars, unfortunately, lose a lot of their angular momentum through the winds that they produce. The amount of winds a star has depends on the metallicity of the star. And so if the star has low metallicity, it will not lose mass through the winds, and it will possess angular momentum. Right, so that is to say that it is possible that GRBs happen in low metallicity environments. If there is such a metallicity threshold, however, gamma ray bursts at high redshifts, the entire population of galaxies evolves to lower and lower metallicities. And so we expect that even if they select environments which has metallicities say below solar, for instance, all galaxies above certain redshift will have metallicities below solar. And so at that point, you run out, there is no cause for that particular bias to exist. That's a very interesting question, and it remains to be seen what kind of galaxies gamma ray bursts select.
In your optical afterglows, how do you know the absorption features are from the host gas in the host galaxy instead of somewhere in the immediate environment from that prior mass loss from the progenitor?
Right. The question is, how do you know that the gas is from the host galaxy? Well, so you expect that. Okay, let me rephrase. When we take a spectrum of a gamma ray burst afterglow, how do we associate the features to the gas from the host galaxy? In this case, we take whatever is the highest redshift system, firstly, but it's possible that objects within the line of sight are also absorbing. So we take the highest redshift system as coming from the host. In addition, you're saying it's possible that there is material just around the star. Most of that material is expected to be destroyed by the ultraviolet and gamma ray radiation from the star itself. So the absorption that we see is expected to be from the ISM. Additionally, it is possible through sort of the equivalent of reverberation mapping, if you will, of measuring the distance to some of these, figuring out the distance of some of these absorption features from the host. It turns out that some of these, as the GRB goes off, it excites certain transitions at certain distances. And so you can see, I don't remember I think it's various excited states of certain elements. You only see them at certain distances. And so we know where those are coming from, and we know that by extrapolation that most of this absorption is actually coming from the ISM.
Other questions? Okay, if not, let's thank Tanmoy again.